So what are we going to do today? We're really going to start thinking about the factors that control our winds. So why they go the direction they go, and how fast they move. And so we're going to talk about things like pressure gradients, the Coriolis effect, which anyone who's had a class with me before knows our little saying, and also friction. So friction is that resistance to movement. That's going to have an important role to play at different heights in our atmosphere. And so the last thing we're going to do today is you're going to get your bit of paper which has the pressures for today. Right now, or sort of at 12 o'clock or so, those were the pressures that we would measure across the US. And you're going to try your hand at a little bit of wind forecasting. You're going to think about which direction the winds are going, and then we're going to compare that with what we see. So this is what you're going to do. You're going to get a piece of paper that looks very much like this, and what you're going to turn it into in your head, hopefully, is something that looks a little bit more like this. Okay? So this isn't today's, because I'm not going to give you the answers. But this is what the winds looked like during Hurricane Sandy when it came ashore in New York. And you can see how strong those winds are. So this map, so that the stronger the line, the larger the line, the faster the winds. And you can see how they're all spiraling into that center there, which was the center of that storm. Whereas over near us, it was a lot less windy at that time. We weren't having the same sort of weather. So really, we're going to look at how you go from having a map like you have to producing something like this, at least conceptually. So why do we have winds at all? So we have winds because there is a difference in the amount of energy that we receive at different latitudes and the amount of energy emitted at different latitudes. So first of all, around the equator, we get much more energy than we emit. And near the poles, we're losing a lot more energy. We're emitting a lot more energy than we're gaining. So around the equator, we have this energy surplus. And at the poles, we have this energy deficit. And we need to move that energy around. And how that is done is with our winds and with the movement of our atmosphere and also the movement of our oceans. Okay? So that's why we have our winds. And if we're going to talk about pressure today, it's worth thinking about it, okay? Anyone who's accidentally been stood on by someone wearing high heels knows that pressure is equal to force divided by area. If you have a really large force in a very small area, like on a high heel or something, then it's going to exert a lot of pressure. And that was the same idea we had with the idea is you don't want to drive your car across spiked tires because all of the weight of your car is going onto a very small area. It exerts a lot of pressure and it can spike through your tires. Okay? And unfortunately for us, meteorologists, people that deal with pressure, are not very decisive about what unit they want to use. And so if you're reading books, if you're looking online, you might find a whole bunch of different units. And so you can see PSI, which is pounds per square inch. If you ever get gas cylinders, then that's often what they are measured in. We get millimeters of mercury, because that used to be how we measured pressure. Torr, pascals, millibars, and we are at 1 atmosphere here on Earth, and that's more useful for when we're looking at other planets. So really the two that you're most likely to see from maps that I give you in homeworks or whatever else are pascals and millibars, okay? So just be aware that there are these different units, and so if I'm asking you to do things like calculate pressure gradients, make sure you look at the sort of legend of the map and see what unit is being used, okay? So how does pressure change? Why does pressure change with temperature? Well, first of all, we have our equation of state. So what our equation of state says is that P, which is equal to pressure, is equal to the density, so how many molecules we have per unit area, times by this universal gas constant, you can ignore it, it's a constant, times by temperature, okay? And so what that means is that with increasing temperature, as molecules get sort of faster, they exert more pressure, okay? It also means that as we get increased density, as we get more molecules per unit area, then we get increased pressure. Okay? And you know that because you know when we blow up a balloon, you get higher and higher pressure within a balloon. You're forcing more molecules in. Okay? And then as we cool things down and warm things up, it changes too. So first, hopefully easy iClicker question of the day. Which of the following would lower the pressure of a gas in a sealed container? Would it be raising the temperature, lowering the density, or decreasing the size of the container? So think about it for a second. Let's see how we're doing. Pretty good. Definitely an easy first iClicker. It gets a little bit more tricky after this. So yes, absolutely. If we're going to lower the value of density in our equation, we're going to lower the amount of pressure. If we're decreasing the size of our sealed container, then what we're doing is basically forcing those molecules into a smaller and smaller space, so we'd be increasing density instead, and so that would increase our pressure. Okay. So I think most people have got this idea, which is good. So, and this is where we got to on Tuesday. I blew up my balloon, and I said, where was the high pressure? The high pressure was inside the balloon. Okay? And so if I let it go, we got movement of air from inside the balloon from high pressure to outside to low pressure. And if I blew my balloon up a little bit and let it go, it might travel a little distance and then fall to the floor. If I blow up the balloon a lot, if I create this really huge difference between the high pressure and the low pressure, if I let my balloon go, it travels a very long way. Okay? Basically, there's a faster wind. There's a greater movement of air when there's a bigger difference. And so we use the term pressure gradient to describe the difference between my area of high pressure and my area of low pressure, and it's divided by a distance. If I have a really extreme change between a high pressure and low pressure really close together, we're going to see a really sharp, strong movement of air. If I have a high pressure over in London and a low pressure here in this room, then even if those differences are quite big, it's a very, very big difference. And so we're not going to see as strong a wind, as strong a pressure gradient forcing that air to move. Okay? So important things is air always moves from high to low, and it also depends on the distance. So now we get into things that are a little bit more challenging. So when we draw plots or draw maps of isobars, because if we want to know what the wind is doing, we really need to see it on a map view. What we're doing is drawing lines where we connect up areas of equal pressure. So for example, if I had a barometer to measure pressure, and I measured pressure here in this room, and it was, I don't know, 1,020 millibars, okay? Then maybe someone in Arizona also measured pressure. It was also 1,020 millibars. We could draw a line connecting those up, and everywhere on that line would measure 1,020 millibars. It's exactly the same as saying I might measure 18 degrees Celsius here in this room. Someone over in Arizona might measure 18 degrees Celsius. We could draw a line connecting those areas of equal temperature. And anywhere on one side of that line might be hotter, anywhere on the other side would be colder. And it's the same thing with pressure. It's just a difficult concept to get, perhaps. And so what I wanted to do is perhaps introduce this lines of equal sort of measure in something that's a little bit easier for us to visualize. And so what we're going to do is think about contour maps. Has anyone here ever seen a contour map or used one when hiking? Anyone seen one at school? This is horrifying. Everyone should learn this at school. At least a few people have seen it. This will be easy for you, but not so much for everyone else. So let's have a look at my little example over here. So have you ever seen something like this on a map? Maybe a few people. Everyone uses GPSs these days. But what we're basically looking at here are lines of equal height. Okay? So if I imagined a nice sort of conical shaped mountain like Mount Fuji or something that's this perfect sort of conical shaped mountain, then what I could do is I could draw lines of equal height, okay, around it. So for example, it's difficult to do in 2D, but if I had, let's turn the light on, you can see. if I had a sort of a mountain like this, okay, so it's steeper on one side than the other, okay, but here's sort of my ground surface. If I draw lines of equal height along here, so here would be 1, so everywhere along that line would have the same height above sea level. And then I might choose to draw another one, maybe 100 meters down, and then another one at 100 meters down, another one at 100 meters down. So this might be my 100-meter contour. Everywhere on that sort of line is 100 meters. This would be 200 meters. This would be 300 meters. This would be 400 meters. So that's looking sideways on at my mountain. Now if we think about what happens if we look down from above, then we'd see something different, right? If I looked down on this mountain from above, instead what I'd see is something like a line like that, sort of going all the way around my mountaintop, and that would be my 400-meter contour line. And then we can see that a little way away on this side is my 300-meter. It's further away on this side, okay? So here's my 300-meter contour line. And then we can do the same for 200 meters, okay? So we see something very different when we look at it from above, okay? So those are basically what we're doing. And so where is the highest point on my mountain? Stupid question, but at the top, in the center, okay? So it would be this point at the top, it should be this point in the center, okay? It's basically in the middle here, okay? It's at the biggest number, okay? But what about where it's steepest, okay? Can you see that one side of my mountain is slightly steeper, the left-hand side? And what do you notice about those lines on the left-hand side when we look down from above? Yeah, they're closer together, okay? So where those lines are closer together, what we're saying is that it's steeper. There's a bigger gradient, okay? So if you were walking down that, you would be walking down a really steep slope. On the other side, where those lines are slightly further apart, the slope is slightly less steep. There's less of a gradient. If you rolled a ball down each side, which side would it move faster down? The left-hand side. It's steeper, it would go faster. And we can use these exact same concepts if we're talking about pressure, okay? When we talk about pressure, we talk about high pressure, which is basically like the top of my mountain. That's the highest number we would measure, okay? And then the highest pressure gradient is where it's steepest, okay? So where those lines would be closest together. So if we go back to my example, okay, I want to show you something really neat. So here is a slightly more complicated example, but you can still see I have maybe like my 100-meter contour, 200, 300, 400, and then this one's again 400, 500, 600, okay? What I can do is I can put another piece of paper across at any point, and I've marked that scale on my y-axis here, okay? And so let's just draw it across, say like this, okay? So what I'm going to do is I'm going to mark a point on my little graph down here whenever I go across a contour line. So the first one I cross is this one, which is my 100-meter contour. If I go down, I can plot a point at 100 meters at this particular distance. If I go, the next one I cross is 200 meters. I could put 200 meters there. The next one I cross is 300 meters. Then I go to 400 meters. But then on this side again, it's 400 meters again. So I'd plot another one at 400 meters. And then I don't really cross a contour. I'm going to ignore that one. I don't really cross another contour till over here. And if we look around, if we sort of connect up the lines, this would be 300 meters again. So here would be 300, here would be 200, and here would be 100 again. And by sort of connecting up these dots, sort of join the dots, it's really kindergarten type stuff, then what we can sort of see is that we can create basically the shape of that mountain using those contours, okay, which is really neat. So my challenge for you is, can you do this yourself? Okay, So basically, that's my little diagram. That's what it would look like if we built a little scale model in 10-meter steps or so. So if I got you to do the same thing between 1 and 2, so you can imagine you're walking from 1 to 2 or looking sideways on, which of my little diagrams at the bottom, A, B, C, D, or E, which of those accurately reflects the shape of the land, the topography? So think about steepness, think about which lines you're crossing, okay? So I'll give you a couple of minutes to think about that. It's a bit more of a challenging question, but I have faith in you guys. Okay, let's take a look and see if we've got this or not. I have no idea how this is going to go. Ooh, good work, guys. Hooray, excellent. Yes, it would be B. Okay, so for those people that weren't quite certain, imagine that you're traveling along. So as you start from 1, you cross 100, so you're going up. Then you cross 200, you're going up, 300, 400. And then you sort of level out for a while, and then you start going downhill again. So 400, 300, and then you start going up again. 300, 400, 500 to higher than you were before. And then you start going down, 500, 400, 300, 200, 100. So there's a little dip in the middle there, and the only one that really has that, and also has a lower peak here and a higher peak here, is B. Okay? So if you didn't quite get that, practice doing what I did. Maybe print it out, sort of draw the little shape, and it won't be perfect, but it's close enough. Great. So you guys get, hopefully, contour lines in terms of altitude. Okay? So now, when we're thinking about pressure, which is this much more intangible thing that's difficult to imagine, we're just using those same ideas. Okay? So when we think about pressure, then we plot these, what we call isobars. Iso means the same, and bar means pressure. So we plot isobars, just like those contour lines measured equal areas of height above sea level. Okay? Then these collect areas of different or of constant pressure. And if we're thinking about how air will move, then we don't want to compare, say, the pressure at the top of a mountain with what's down here at sea level. Okay? It's not going to affect our sort of patterns of movement. And so what we plot is sea level pressure. So for example, if we wanted to plot sea level pressure for LA, then in downtown LA, it's pretty close to sea level anyway. It would probably be close enough. But if we then wanted to take into account the mountains around there, then as we go up in the atmosphere, remember we have less and less air molecules, our density decreases. So if we want to plot basically consistent data, then we need to take into account this extra height, and so that drop in pressure that would result. So what we do when we're plotting sea level pressure is we're basically taking into account the different altitudes of different cities and different mountain ranges wherever we're measuring pressure, and adjusting it back to what it would be if that location was at sea level. Does that make sense? Sort of? No? Again? Yes? Okay. So down here at sea level, we have a higher pressure, and as we go up, because there's less and less weight putting force down, our molecules get sparser and sparser. Air is compressed down here at the surface, and that density decreases as we go up in the atmosphere. And so if we were to measure the pressure in downtown LA, it would be much, much higher than if we went to the top of a nearby mountain. But if we want to think about the way that air is going to move, we don't want to be plotting just basically differences that we see in pressure due to altitude. We want to see differences in pressure due to other factors. So what we have to do is say, take that measurement from the top of the mountain and say, I know that we're this height above sea level, so what I'm going to do is make an adjustment that means that I'm going to change that pressure to be what it would be if that location was actually at sea level. So we just make a mathematical adjustment to that number. Okay? So what we end up with is a map of what you would measure, what pressures you would measure if you were at sea level all the way across the US. And you can see that wherever we have higher numbers, the numbers on here are really small. But for example, here we have 1,020 millibars, okay? And so we call this a little center of a high pressure, okay? It's a high number, it's high pressure. Up here you can see we have maybe 1,004. It's a little center up here of low pressure. Over here we have an even lower one. We have something like 980. So that's really, really low pressure, okay? So we're not looking at how close or far those bars apart. We're just looking at the absolute number to define where our high pressure is and our low pressure is, okay? So thinking back to what we said about how steep areas are and what those contour lines look like when there's a big gradient, a steep gradient, where is the biggest pressure gradient on this map? And thinking before about my balloon and which way air moves, which way would the wind flow across that? Okay? So think for a couple of seconds, consult with your neighbor. Where is the biggest pressure gradient on the map? So let's take a look and see how we're doing. Slightly less good this time round, but it's still the correct answer. So why did you pick B? Yeah, the lines are closest together. And that's really as complicated as it gets, guys, okay? And what those lines being really close together shows you is that there's a big change from a high pressure to a low pressure over a very short distance. Okay, that's what those lines being close together implies. And so for those of you that picked C, okay, what you're picking there is the biggest pressure, okay? So you're not looking at the biggest change. What you put for C is the biggest pressure. So you're right that that's where you would measure the highest pressure, but that's not where the gradient is the biggest. And people get that confused a lot. So it tends to be one of my favorite exam questions. So make sure you're clear about the difference there. Okay. So how about which way would wind move across that pressure gradient? Would it go from south to north or from north to south along B? North to south, why?
Because it always goes
high to low, yeah. Okay, again, it's really not as complicated as people try and make it. So if we have a low in the middle there, okay, it's almost like a low in topography. If you put something like a ball on the edge there, it would roll into the middle. And that's what air is doing. It's going from higher to lower, okay? And so air would move inwards all around that low. Okay, does that make sense? Yeah, good. So, key thing to remember, when we have closely spaced isobars, we have fastest winds, we have strongest winds. When they're really far apart, we don't have very strong winds, okay? Because in order for air to move, there has to be a pressure gradient. And so where there isn't very much of a pressure gradient, we don't have very strong winds. So now let's think about actually, say, an example. So do you remember that my pressure gradient is equal to the high pressure minus the low pressure divided by distance. So on my map behind there, okay, if we count, I'm not very good at geography, but if we look roughly where New York and Boston is, and I'm going to embarrass myself now. So that's sort of roughly Boston, right? Maybe? Yep. And New York is somewhere down here, right? So it crosses two isobars, okay? There's probably, and each of those isobars is 4 millibars, okay? So we see a pressure difference of 8, okay? So our pressure drop from New York to Boston is 8 millibars, and the distance is about 350 kilometers. So if you do the math, then what number we get for our pressure gradient is about 0.02 millibars per kilometer. It's not that big. That these pressure gradients tend to be very small numbers, okay? And so I wanted to show you a little bit of a bigger pressure gradient. This is, if you can see underneath this map, there's a lot going on here. But this is the East Coast running down here, and this is Florida down here. And the rain shows in the different colors. This is sort of rain. And you can see how closely together those isobars are packed there. So what do you think this might be? Hurricane, absolutely. So this is a hurricane, okay? And so we can do the same thing. We can work out the pressure gradient. So the pressure gradient, maybe over the same sort of distance, might be 28 millibars instead of 8. But that still means it's only about 0.08 millibars per kilometer. But I don't often give career advice, but this is one time I might. So why you don't want to work for the Weather Channel? So apart from a degree in stating the obvious, that's what that sort of pressure gradient means. It's really very, very strong, and we don't often see winds that strong here. But he's a big dude as well. It takes a lot to carry him away. There's no way I'd be standing in that sort of... and so, yeah, these pressure gradients, they don't sound a lot, but they are. So I have a question for you. If we went back to New York and we measured the pressure difference between the base of the Chrysler building and the top, then we would see a pressure drop of 40 millibars. And that's just a distance of 319 meters. And so our pressure gradient there would be 125 millibars per kilometer. So why are we not all being carried upwards every second by intense vertical winds? What's acting in the other direction? Gravity, absolutely. So we don't experience really intense vertical winds. We don't actually see much vertical change at all unless we get this convection going. And that's because most of the atmosphere is in what we call hydrostatic balance. So there are two things going on. First of all, we do have this very intense pressure gradient from higher pressure down here at the surface to lower pressure further up. And so, as we saw, air should be rushing upwards. But we have gravity that's acting against that. And so what happens is that the atmosphere ends up balancing out, okay, apart from in a couple of locations. And so we have what we call hydrostatic balance. And that's just that our gravitational force is equal to our vertical pressure gradient force. It doesn't stop winds moving sideways, but it does stop these sort of intense vertical winds. Okay? Does that make sense? Yeah? Good. So, let's think again about what happens in our atmosphere. Okay. So, I have two basically fake air columns. So just imagine a sort of a column of air, and one is in a warm location, and one is in a cold location. And you can see at the base of both of these air columns, both at the bottom of the warm air column at Earth's surface and the bottom of the cold air column at Earth's surface, we'd measure the same pressure, maybe 1,000 millibars or so. But then that different temperature in those different places affects how much drop in pressure we see as we go up in the atmosphere. And that's because in my cold location, then those air molecules don't have as much energy. They're not moving around so fast. They tend to occupy a smaller space. They're packed closer together. And so if you imagine, if I went up a certain distance in the atmosphere, I would be, say, if I went up to the top here, okay? So if I look here, if I measured pressure up here, I would only be feeling the mass of these molecules above whichever line I choose. Okay? And a lot of that, molecules in the atmosphere are actually below that line. So I'd see quite a big change in pressure as I went upwards. Okay? If you pick the same location and you went across to, say, the warm air column, so over here, well now, all of those molecules have more energy there, they're spread out a little bit more, and so for the same height in the atmosphere, there are more air molecules above my line, okay? So they're going to be exerting more weight downwards, and so I'm going to feel more pressure at that same altitude in the warm air column than I did in the cold, okay? And it's just because here, there are fewer molecules left above. Here, there's still quite a lot of molecules left above, okay? And so as we go up in the atmosphere in a cold air column, there's a very, very rapid drop in pressure as we go up. In a warm air column, that happens more gradually, okay? And so we can think of that as being like where the Earth is. So on this side, my warm is around the equator, around the tropics. Up here in the cold area, we have the high latitudes and the pole, okay? And so if we pick one particular pressure, okay, and think about how high we would have to go up, in our warm air column, if we wanted to go from, say, 1,000 near the surface to 500 millibars in the atmosphere, we'd have to go up a lot further before we hit that pressure, okay? So that we might have to go up maybe 5,600 meters, 5 kilometers up before we hit that 500 millibars. But if we go up to our cold end, at the sort of north of North America, then you can see if we tried to find where in the atmosphere that level where we'd measure 500 millibars is, we wouldn't have to go up as far. A lot more of those molecules are packed down closer to the surface, and so we see a much faster change in pressure, much faster drop as we go up. So that level is closer to the surface, okay? And so we can also think about that in this way. So again, here is down here near my tropics, around 30 degrees north. At the other end, on the left-hand side, we have 80 degrees north, so up near the pole. And you can see that we've plotted those different heights where we'd hit different pressures. So down at the surface, we're still at 1,000 at both locations, but we have to go further up on the warm side to hit 900, further up to hit 800, further up to hit 700 than we would in the cold side. And what does that do? It means that if we pick any one particular altitude, say 2 kilometers or 3, then what we have is a pressure gradient. Because say if we went sort of 3 kilometers up in the atmosphere and we measured a pressure of 800 here in our warm air column, well, over here at 80 degrees north, we'd actually have 700 millibars. So what we have is a pressure gradient, a difference between this high pressure and this low pressure. And you can see that as we go up in the atmosphere, here there wouldn't be that big a change between the warm and the cold. But as we go further and further up, then that line gets steeper and steeper and steeper. There's a bigger and bigger change. It basically is a cumulative change as we go up. And so our pressure gradient force gets bigger and bigger and bigger and bigger as we go up in the atmosphere. So what would that suggest to you about winds high up in the atmosphere? Would they be weaker than at the surface or much stronger? Stunned silence. Much stronger. If we have a bigger pressure gradient force, it's going to be stronger. Okay? So we have relatively weak winds here at the surface. As you go up in the atmosphere, we get much, much stronger winds. Does that make sense, or do you need me to go through that again? One more time? Yes? Okay. So if we look at any one particular altitude as we go up in the atmosphere, then what we want to see is there a difference between one location and the next? Is there a pressure gradient that is going to force air to move? And the answer is yes, because in warm air columns, okay, if we pick any one particular altitude, there's going to be more air pressure there than there is in a cold location. And so if we think really big scale, like on the whole Earth scale, then near the equator, if we go up 5 kilometers in the atmosphere, we're going to see really high pressure compared to, say, at the poles. Okay? And as we go up in the atmosphere, that difference gets more and more. At the surface, we're the same. By the time we get really high, there's a really huge difference. Okay? And so down here at the surface, if they're the same, there's no pressure gradient, air isn't going to move. But high up, where there is a really big pressure gradient from between high pressure in the warm place to cold, or low pressure in the cold place, we're going to see a strong pressure gradient, and that is going to force air to move. It's going to try to go from high in the warm place to low in the cold place. Does that help a little bit? Yeah? Okay. So there are a few things just 3 things, in fact, that influence winds. The first is our pressure gradient, and we've talked about that. We've talked about vertical, that we don't see strong vertical winds because we're in this hydrostatic balance. We see horizontal, though, because of different changes in pressure. The second thing that influences our winds is the Coriolis effect. And before we get started on this is a pretty challenging topic. And for those of you who had classes with me before, you know that this comes up again and again. This is something that is really important for how the Earth works. But it is a difficult thing to get, and it is a difficult thing to explain. And I wanted to show you what happens when you ask a whole bunch of meteorologists to explain the Coriolis effect. So these are British people again. I always seem to find British videos.
A difficult thing to understand, I think.
It's to the left. Oh, is it to the right? I just get it then.
I'll set the right asking.
So the idea is that these are people who work with this every day, and they find it a challenge. So don't panic. It sometimes takes a little bit of thinking about, but we'll get there. And we're not going to get into the hardcore mathematics of it. I do have an explanation if you would like to do that. But we are going to at least try and develop a functional knowledge of the Coriolis force. Okay, so what is it? It's an apparent force that happens because the Earth is spinning round. Okay, so the Earth is spinning. And so what happens is it doesn't affect the speed of our wind or our object or anything else, but it does affect the direction. Okay, so has anyone ever played the sniper game? Someone told me that there's like a sniper video game and you need to take Coriolis force into account? No? Okay, I thought it might be a popular one, but obviously not. So, never mind. So let's think about the Earth. So the Earth is spinning, and we rotate once every 24 hours. That's what gives us our day and night. And so let's think about what that means for, say, a person stood on the equator. Okay? If a person is stood on the equator in the middle of my image there, then that means that in 24 hours, they have to travel all the way around and back to where they started. Okay? And so if we look at what that circumference of the Earth is, it's about 40,000 kilometers. And they have to do that in 24 hours. If you do the math, that means that they're traveling at about 1,670 kilometers per hour, or 1,000 miles per hour. You're probably traveling sideways at about maybe 800 miles an hour or something like that, okay? It's fast, or a little faster than that maybe. If we go up to maybe the pole, if you stood right at the North Pole, what would you have to do to get back to the same place in 24 hours? Okay? You're probably not going to be traveling very fast, okay? And so this difference in the speed at which things are moving on the Earth's surface is what is causing that Coriolis effect, okay? So if you go to the Antarctic Circle, the Arctic Circle, then you see you have less distance to travel in the same amount of time. You're traveling less fast, okay? And you all know what happens if you try and sort of throw something into a moving car or something like that, or at a moving car. If you throw where it is right now, then by the time your object reaches it, the car's moved on, you miss, okay? Or if you throw something from a moving car, which you should never do, obviously, then you can see it sort of curve away. It's actually traveling in a straight line, but to you, it looks like it's curving away, okay? So, what does this mean for us? It means that if an object is moving along at the equator, okay, then it's moving very, very fast. It's moving at the fastest sort of speed that anything is going on Earth. If it then moves off the equator, okay, and if it's not attached to the ground, if we're talking about wind or water or a plane or anything like that, okay, then as it moves off the equator, it's going to be moving sideways more than the ground underneath it is, okay? So instead of traveling just sort of straight up, what it's actually going to end up doing is swerving, okay? It's going to end up bending. So let me say that again. If you're on the equator and you're moving very, very fast, if you then move off the equator and you're not sort of attached in some way to the ground surface, then you're going to still be moving in this direction much faster than the ground is underneath you, and so you're going to seem like you're moving, you're going to get deflected in this direction. Does that make sense? Maybe? Okay. So, we have a golden rule, and everyone who's been in my classes before knows, I am from the northern hemisphere and I am always right. Okay. I am from the northern hemisphere and I'm always right. In the northern hemisphere, the Coriolis force deflects things to the right of the direction of motion. Okay? So if you look at my little arrows there, if I move from the equator towards the North Pole, I get deflected to the right. Okay? But remember, you always have to look along the way you're traveling. So if you now look at something that would be traveling from the North Pole towards the equator, it's coming in this direction. Which way is it being deflected? To the right still. Okay? If you look down in the direction of the arrow, always look along the arrow, it's actually going to the right. If we look now at the southern hemisphere, if you go from the South Pole towards the equator, it's being deflected to the left. So in the southern hemisphere, everything is deflected to the left instead. Okay? And again, if we're going from the equator to the South Pole, if you look along the direction of the arrow, it's still going left. Okay? So in exams, what I want to see is I want to see people turning their pages around so that they can look in the direction of that arrow. Okay? Always look along the arrow and you'll get it right. So, the Coriolis force, the strength of that force depends on a few things. If you're throwing a baseball at someone, even if it's going really fast, you're not going to have to take into account the Coriolis force. Okay? So the strength depends on where you are in terms of latitude. It's going to depend on the rotation rate of the planet, which fortunately for us is pretty much a constant. We don't need to worry about that. But then the speed of the moving object. Okay? If a snail is moving along or something like that, it doesn't need to bother. But if you're sending a continental missile at someone, then you really want to make sure that you've taken the Coriolis force into account. Okay? If you're on a plane, you want to make sure you've got the Coriolis force right as well. And so moving objects are deflected to the right in the northern hemisphere, the left to you in the southern hemisphere. I have a problem with left and right, so do check me sometimes. But the easiest way I found of remembering it is just to say, I'm from the northern hemisphere and I am always right, because I am. So, for those people that would like a slightly more mathematical explanation of things like conservation of momentum, then there's a nice YouTube link there. It's not necessarily a bad idea, even if you sort of watch it and get scared and sort of don't choose to do any more. There's also some nice visualizations at the top. And there's a fun little game, so I thought we should play the fun little game. So, let us find. So what is happening here is that you are an airline pilot, well not an airline pilot, a fighter pilot, and you have been told to fly towards your aircraft carrier that is hovering around in the sea somewhere, okay? And you have three options. You have the three red dots there. So you can choose to aim for the one on the left. If you want the one on the left, choose A. You can aim for the center, B, or you can aim for the one furthest on the right, which is C. Okay? So think about the rotation of the Earth, where he's going to end up, and see if you can actually land him on his aircraft carrier. So, what do you think? A, B, or C? Okay. So let's see whether we get this right or not. Oh, so it was a close race anyway, but the majority voted C. So let's click C and see what happens. Bad things happened. Okay, so let's see if we can try this again. So, we're still in the southern hemisphere. So now you've had a chance to think about it. So here's your plane. I'm not quite sure where he's taking off from, but here's our aircraft carrier. So again, A on the left, B in the middle, C on the right. Think about how fast he's going, which way he's going to be deflected. Okay? So let's see if we can more safely land this time around. So we have a clear winner this time for A. So let's see if we drown our poor pilot. Woo! Okay, so well done for those people that got it. I think this little game really helped me grasp what was happening a couple more times through, and you get a much better sense of what's happening. So it'll bounce you between the northern hemisphere and the southern hemisphere and which way the plane is going. So if you're struggling with this, have a little play with this. It's a fun game. You can challenge your roommates or your parents to beat you. Okay. So for now at least, just mainly remember, I want you to remember two things. I want you to remember that in the northern hemisphere, things get deflected to the right. In the southern hemisphere, things get deflected to the left. And that the strength of the Coriolis force depends on how fast you're going. So the faster you're going, the stronger that Coriolis force is. Okay. Because the last thing that we're going to talk about is friction. And we're going to talk about 3 different layers in the atmosphere. So the first that we're going to talk about this once and never again is the laminar boundary layer. And that's basically the 1 or 2 millimeters, so like that much, hardly anything, between the ground surface and the rest of the atmosphere. Okay? And so the friction there is obviously really, really strong. It's very much in contact with the ground surface, so it's important for transferring heat. But in terms of the wind, we don't really care what the winds are in the 1 or 2 millimeters above the ground surface, okay? We're not going to talk about it. The other 2 things, though, that we are going to talk about is the planetary boundary layer. So the planetary boundary layer is the lower 1.5 kilometers, and that's where friction is important. So what sort of things might cause friction with the wind? I think I heard someone mutter it. What do you see moving outside and interfering with the wind? Trees, okay? So trees, buildings, mountains, all of these things are going to interfere with the movement of the wind. They're going to cause friction, okay? They're going to interfere with the movement of those air molecules. But that's important down here in the lower 1.5 kilometers, but in what we call the free atmosphere above 1.5 kilometers, then there really just isn't much stuff for the wind to bump into, okay? Up there really aren't these surfaces that are going to interfere with the movement, and so there we can really safely ignore friction. We can say that friction isn't important there, okay? And so where do you think the Coriolis force will be stronger? Do you think it'll be down here in the planetary boundary layer, or do you think it'll be in the free atmosphere? Okay? Yeah. It's important in both, but in the free atmosphere, it's going to be stronger, okay, than down here at the planetary boundary layer. So now what we're going to do is have a play around with these 3 factors and think about really how they go about changing our wind patterns that we see in terms of horizontal patterns. So we're going to do the easiest one first. We're going to think about the free atmosphere, that stuff above 1.5 kilometers, where we can ignore friction. So we only have 2 things to think about. We have the pressure gradient force, okay? Without a pressure gradient, air isn't going to be moving. And the second thing is we have our Coriolis force that we need to take into account. So here's my diagram here, but actually I'm going to take some time to draw this, because I think it makes more sense if you see it drawn out. So grab your pens and paper. I will switch over. So, first off, we're just going to think about a really easy example. We're going to go from, here are going to be my isobars. They're nice straight isobars, okay? And we're going to go from high pressure here to low pressure up here. So just like we would do high up in the atmosphere, where we're seeing higher pressure in our warmer air column near the equator, lower pressure in our cold air column near the pole. There we go. Okay, so which way would air move across my pressure gradient? Will it go from the top to the bottom or the bottom to the top? Bottom to the top. It's going from high to low. Okay? So if I imagine a particle or a sort of a little package of air, okay, and it's going to start off here, okay, my little package of air is going to start moving because there's a pressure gradient force. And that pressure gradient force wants it to move in this direction. Okay? Does that make sense? Yeah? But we also have something else. So this is what I'm going to call pressure gradient force, PGF, the pressure gradient force. But what was the other thing we have to take into account? The Coriolis force. Okay? And in the northern hemisphere, the Coriolis force always acts at 90 degrees to the right of the direction of motion. Okay? So if we had to plot a little arrow that's going at 90 degrees to the right of that, that's my Coriolis force. Okay? So what is my wind actually going to end up doing? Which way is it going to go if it's feeling both the pressure gradient force and the Coriolis force? Yeah, it's going to go in between those. Okay? So my wind would actually end up traveling in this direction. Okay? So now let's think again. Now after a certain amount of time, my parcel of air has moved in this direction. Okay? It's still going to keep moving because there's still a pressure gradient force. Which way is that pressure gradient force? Has it changed? No, it's still exactly the same as it was before. Those isobars haven't changed. So my pressure gradient force is still in this direction. But now, where is my Coriolis force acting? It's acting at 90 degrees to the right of the motion. Okay? So what is that going to be? Is that going to stay the same? No, it's not going to stay the same. If we look at where 90 degrees is to how that wind is moving, it's now that way. Does that make sense? So my Coriolis force is that way. So which way is my wind going to end up moving? Is it going to carry on in a straight line, or is it going to change more? It's going to change more. It's going to end up more tilted, right? So we're going to end up something more like this, perhaps. Okay. So now let's think about it again. So has my pressure gradient force changed? Has my pressure gradient force changed? No, still acts in the same direction. Which way is my Coriolis force acting now? Down that way, 90 degrees to the right of the direction of motion, which is this way. Okay? And so which way does my wind end up moving? Becomes even more tilted. Okay? So, now let's think about what happens here. Which way is my pressure gradient force going? Up. Still the same. Which way is my Coriolis force acting? Straight down. It's at 90 degrees to the right of this, which is that way. Which way is my wind going to go if those balance out? It's just going to go straight. It's going to go parallel to my isobars. So this is how wind travels. If I extend my isobars out a little bit, okay? So even when our wind starts moving with that pressure gradient force, it's actually going to end up traveling parallel to these isobars, because where this pressure gradient force equals out with this Coriolis force, now we're just going to travel in a straight line until either one of these, or until the pressure gradient force changes direction. Yeah? Absolutely, and we're going to come back to the jet streams later on in the class. But basically, this is exactly what happens high up in the atmosphere. We have this really big pressure gradient, especially exactly where the jet streams form, which is quite close to the pole. There's a big difference in temperature across that particular latitude, and it just ends up going sideways. And we might get little bends in it, but it tends to go in this direction because of the Coriolis force and this pressure gradient between the equator and the pole. Yep, absolutely. And so that's why in planes, it's way quicker to go to Europe than it is to come back from Europe because you can get into the jet stream and fly at these high altitudes. And so if you ever notice, there's like an hour difference in the travel time. So we'll come back to this much later. Yeah?
If the paraglider had like an oxygen tank, you could just make it all the way.
You have to go really high up. It would be very uncomfortable because it would be very, very cold as well. So usually they don't get quite that high. You also wouldn't be able to see much cool stuff. But when people tried to go around the world in balloons, they went pretty high as a result. So, but yeah, we'll talk more about that. So is everyone clear about this idea, though, that we end up traveling parallel to our isobars? Yeah? Good. So this is a nice idea, but our isobars don't often look like this. They're not often completely parallel straight lines. Our isobars are often a bit more bendy. And so it's a bit difficult for things to go completely parallel to isobars if they're sort of diverging and converging. And so this is what our really high-level winds tend to look like a little bit more. They have this sort of, they still go pretty much parallel to our isobars, but they might sort of diverge and converge a bit. And so we call these gradient winds. So the last one, the ones I talked about there, these are called geostrophic winds, okay, where the pressure gradient force and Coriolis force balance out. Slightly more realistic are these gradient winds, and this includes the effect of centrifugal force, okay? But that's really as far as we're going to go with that concept. So I have a really good question for you. So we have highs and lows in our atmosphere. And what I want you to tell me is, this is up in the free atmosphere, thinking about that air goes from high to low, and you're from the northern hemisphere, so you're always deflected to the right, okay? So see if you can work out the resulting air patterns that would happen in the northern hemisphere. So which two panels show circulation in the northern hemisphere? So think about it for a second, speak to your neighbors. Okay, are there any last answers for me? This is also one of my favorite exam questions. Okay, let's take a look and see how we did. Not great. Okay, so let me show you how to work it out for one of them, and then that at least gives you a 50-50 chance, okay? And you're making it much more complicated than it needs to be, I promise, okay? So you don't need to memorize this stuff because you know that air goes from high to low. So is air going to be traveling into or out of my high pressure? Out. As it travels out, which way is it going to be deflected in the northern hemisphere? To the right. Okay? So it doesn't matter because even if you look at it this way around, okay, it's going out. Remember, you always have to look along the direction of travel. It's going to the right, okay? So can you do the same thing for the low? Is it going into or out of the low? So which way would it be deflected? So which way would it end up traveling around? So I'm going to go back and I'm going to ask my question again, okay? Okay, so let's take a look and see how, whether we got a more of a consensus this time around. We did. So the 65% would be right. So for those that put D, good try, okay? It was a 50-50 chance. So let me go back and let's complete that last one. So in this case, we have air going into a low, okay? If air is going into the low in the northern hemisphere, which way will it be deflected? To the right, and so it's going to go this way. In, and to the right, in, to the right, in, to the right. Okay? So have a think about that one. Every time people try and memorize this stuff, and it's a complete waste of your time, because you know if you go from high to low, okay, and it's to the right in the northern hemisphere and the left in the southern hemisphere. Okay, so now let's think about something a bit different, okay? So here's a little summary for those people that didn't quite get it, but do try and work it out. I just need to introduce a little bit of terminology. If you've ever heard of cyclonic or cyclones or anticyclones, what we're talking about is whether there's high pressure or low pressure. If there's a high pressure in either the northern hemisphere or the southern hemisphere, we call that anticyclonic or anticyclones. If there's a low pressure in either the northern hemisphere or the southern hemisphere, we call that cyclones or a cyclonic flow. Okay? So we'll get used to those terms. So now let's think about what happens in the boundary layer. So in this layer it gets a little bit more complicated because we have to take into account our third factor. We have to take into account friction. What is friction going to do to the speed of my wind? It's going to slow it down. What is slowing down my wind going to do to the amount of Coriolis force that my wind feels? It's going to be weaker. That Coriolis force is going to be weaker. So what do we have left that's going to sort of win out, basically? Because that if our Coriolis force is weak, then our pressure gradient force and our Coriolis force aren't going to balance anymore. One is going to be stronger. That pressure gradient force is going to be stronger. And so instead of going along parallel to those isobars, now that pressure gradient force wins and it basically pulls it across. Okay? So if we go back to thinking about the little diagram I drew before, so in this case, if we had the same thing, okay, my pressure gradient force is here, my Coriolis force will only be very weak. And so actually, that wind will travel much more like this. And so here, it'll still feel very strong pressure gradient force. Coriolis force is very weak, and so it tends to, so instead of being really strongly deflected and moving parallel, it will tend to keep going across isobars. Okay? So that's really the only difference. It'll still deflect in the same direction, but it's much more likely to move across these isobars. And so this is the difference that you'd see. So on the left is what we'd see in the free atmosphere up high, where our pressure gradient force and our Coriolis force balance out. We end up seeing movement of that air parallel to our isobars. On the right-hand side, you can see what happens down much lower at the surface. You can see that in an anticyclone, we're going from high to low, and instead of that wind being really strongly deflected and moving around and around and around, it actually, that pressure gradient force that's pulling it out of that high pressure wins. And so that wind tends to spiral outwards across those isobars, but still in the same direction, still in the consistent direction. And the same thing is true for cyclonic, okay, for that low pressure. Now our pressure gradient is trying to force air into the middle or pull air into the middle of that low. And before, the Coriolis force sort of caught it and it just kept going around parallel to those isobars, whereas now that pressure gradient force wins and that air moves into the middle. So I have a little question at the end. What creates these areas of high and low pressure to begin with? I'm not going to tell you now, but we are going to talk about this later in the class. So these ideas, these aren't just something that we're going to talk about today and never mention again. These are really important ideas for how the atmosphere functions. So don't forget them. So my diagram here is not of tornadoes. It was drawn in a very strange way, I think. What we're showing here is what happens differently at the surface compared to high up in the atmosphere at these high and low pressures. So you can see at my high pressure, we have at the surface, if we think back a second, at my high I have winds moving outwards in all directions at the surface, okay? And so we have winds moving outwards from that area of high pressure. Is all of that air going to move away, and are we going to be left with a vacuum in the middle and everyone's going to suffocate and die? No. Okay. So that's not going to happen. We have to replace that air from somewhere. Okay? And where we replace it from is much higher in the atmosphere. So if we have air moving outwards in all direction at the surface, we're going to have to replace that. We can't replace it from underneath. We're at the ground. We can't replace it from the sides because air is moving outwards. The only place we can bring more air from is above. Okay? So air above sinks down to replace that air that is moving outwards. And we have the reverse going on in our low pressure system. So in our low pressure system, we have lots of air moving in. It's not going to keep moving in forever and pile up it's going to have to go somewhere. It can't go down, but we're at the surface. We've got winds coming in from all directions. The only place it can go is up. Okay? And this has a very strong control on our weather. This is why in high pressure areas we have lovely sunny skies, and why in cold or low pressure systems we have different weather. And that's because as those winds move apart, as we pull down air from higher up, as that air comes down, it warms up. And as it warms up, it basically dries out a bit. And so we never create clouds, we don't get much rainfall and precipitation. But at low pressure systems, where we're pulling all of this air in and it's then moving upwards in the atmosphere, as it moves upwards, it cools down. And so we create clouds, we create rainfall, and we'll talk much more about that next week. So, now it's time for you guys to do a little bit of work, but it's going to be really helpful because these are sorts of things that we're going to look at again and again, and so I wanted you guys to have a chance to do this. So, on your map, I want you to think a little bit. Does everyone have one, by the way? No? If we have spares, can we pass them around? TAs, can you track some down for me? So, you can see, sorry, could I borrow yours for a second? I forgot to take one. So you can see that on my map, which is from today, I have, and this is sort of a sea level pressure, so we're down in the planetary boundary layer, right at the bottom of the surface of the atmosphere, okay? So you can see that we have different numbers on here, okay? These are in pascals rather than anything else, but let's not worry about that. So what I want you to do is think about a couple of things. So first of all, think about where would you see the strongest winds? And we're going to check and see if you're right. Where would the high pressures be? You know, we have those high pressures or low pressures in circles. See if you can mark those in. Where do you think it might be raining? Where do you think it might be slightly more sunny? Okay? And you can do all of those things now. So see if you can sort of mark in, for example, like around here. We're at 1012. Outside it's 1016. So is air going to be moving into or out of this area? It's going to be moving into. As it moves into that area, which way is it going to be deflected in the northern hemisphere? To the right. So it's sort of moving in, and I can't do things upside down, to the right. So it might be sort of spiraling like this a little bit. So see if you can do that for some of the different areas on your graph or on your piece of paper here. And I will show you that same map we had at the beginning showing Hurricane Sandy. I'll show you what it is right now, and you can see if your predictions actually hold true. Okay? So I will wander around, as will the TAs. If you have any questions, let us know. Oh, I stole your piece of paper. Thanks. Oh, it's fine. I think there'll be some spares back here, so I'll grab them. Sorry?
The questions back up? Or what you want?
Oh, yes, of course. So where do you think I might see the strongest winds? Where on here? It's going.
Be over here where the highest pressure gradient is?
Absolutely. Would it be only here? Is there anywhere else that we might see strong winds?
Over here too?
Maybe.
It's a little bit closer than the other ones.
Yeah.
Here maybe?
Maybe a little bit there. I think up here as well.
Sorry, didn't see any numbers. I'm like,
It's all right. So yeah, it's sort of getting used to seeing that. So I think that might be a good prediction. What about which way air would be going into here? Which way do you think would it be going, outwards or inwards into this area marked 1020 here?
It would be going inwards since it's going from high to low.
Yeah. And so which way would it spiral?
It would go, well, you would be looking from here, so it would go to the right. Like
Yeah,
this
so you can
way.
have a look and see if that's right. Okay.
Yeah.
Looks good. So where do you guys think it's going to be windiest on my map? I'll come back to you in a sec.
Over here.
Yep, over here. Okay. What do you think might be happening here? Is it going to be moving into here or out of here? Into. And which way do you think it's going to be spiraling?
To the right.
So you think?
Yeah.
So there you go. Draw it on. See if you can.
Wouldn't it look the same as this way over here? So we move this way and then go downwards. Oh, wait. Coriolis style. 9 degrees. Shoot. Just like the other way. I don't know.
Maybe. Okay, that's fine. We'll think about it. Okay, we seem to be losing a few people. Shame on you, this is useful. So let's think about this. So if I put on up here, so first of all, where do you think my highest pressure gradients are going to be? Where is it going to be windiest when I show you the map? So up here maybe? Yeah? Anywhere else? Great Lakes, perhaps? Maybe over here? Okay. Where do you think it's going to be least windy? Yeah, somewhere over here, perhaps? It might depend, because we do have sea breezes that might not behave as they should over here. So let's think about here. What is this? Is this an area of low pressure or high pressure? It's a low. Okay. What about over here? Is this a low pressure or high pressure? High. So let's think about how air might be moving into the, or I just told you, is air moving out of or into that area? Into. Which way is it going to spiral? Yeah, like this. So it's going to be moving inwards and to the right, okay? Inwards and to the right, inwards to the right, inwards to the right, okay? So let's see if we're right about that. Which way might air be moving in this direction? Is it going to be moving into that high or out? And is it going, which way is it going to spiral? Yeah, absolutely. So it might be moving more like this, okay? So, shall we see if we're right? Let us go back to my lovely wind map. And instead of looking at Hurricane Sandy, we're going to look at today. So it's slightly different scale map, but here's our low pressure area over the Great Lakes on your map. And you can see it is in fact low pressure, air is moving into it, and it is spiraling inwards, right, in the same direction we said. Over here, we had a high, and air is moving outwards, and it's moving clockwise. Over here, it's not quite as sort of calm as we thought it might be, but definitely somewhat. Okay, great, thanks guys. We'll continue on Tuesday.